think we can get started, Dr. Howe.
Sure.
Yeah. Hello, everyone. Welcome to this week's edition of the Data-Driven Learning and Control Seminar Series. And I'm Nishant, and I'm pleased to introduce today's speaker, Professor Jonathan P. Howe. He's going to present on the topic Robust Planning and Learning for UAVs. A little about Dr. Howe. He is currently the Richard C. McLaurin Professor of Aeronautics and Astronautics at MIT, and he did his undergrad back in University of Toronto, and then he did his master's, PhD, and also his postdoc at MIT. And before joining MIT in 2000, he was with Stanford University. He's a fellow of the IEEE and AIAA, and he was elected to the National Academy of Engineering in 2021. Dr. Howe has served as the editor-in-chief for IEEE Control Systems magazine and is currently an associate editor for the AIAA Journal of Aerospace Information Systems and IEEE Transactions of Neural Networks and Learning Systems. And he also was elected to the board of governors in IEEE Control Systems Society. And other than that, he's also serving as a scientific advisory on the scientific advisory board with the USAF Air Force. And Dr. Howe's research focuses on robust planning and learning under uncertainty with an emphasis on multi-agent systems. And he has contributed to the MIT's team for DARPA Urban Challenge back in 2007. And he has been recognized with a plethora of awards, including Distinguished Member Award at the IEEE CSS and Intelligent Systems Award at AIAA Association and the Institute of Navigation Work Award. And a number of his research work has garnered Best Paper awards in various conferences, top robotics conferences like the IROS and ICRA. And he also received an Amazon Machine Learning Research Award in 2018 and 2020. And without further ado, I'll pass on the mic to Dr. Howe.
Great, thank you. Let me try sharing slides here and make sure this works.
Yep.
Hopefully that's working all right. All right, great, and thanks for the introduction. So the plan today was to give you an update on the things we've been doing. So the title says Robust Planning and Learning for UAVs, and it'll cover a bunch of different topics, some of them of different maturity levels than others, but spanning probably the past 3 years in terms of research and a particular focus of the group. And towards the end, I'll sort of begin to spill over into sort of other topics we need to think about now and build on the current things we're doing. You'll see Koda's name show up quite a bit in this work. He's not the only student working in this area, but he's well, that'll be with the slides. So he's the name that gets put on the front page here. All right, let's get started. So we've been working quite some time thinking about sort of multi-UAV trajectory planning, specifically in dynamic worlds, not just because there's objects moving around, but there's also because there's other planning agents in the world. And so we've done this outdoors. We've also done it indoors. If you've been to MIT recently, you may have seen this new lab facility we built back in 2018. But basically, it's a nice high bay, about 20 feet from office. It's about 90 feet long, 30 feet high. And so it's good size for flying around a whole bunch of different UAVs. And so I'll talk about this mission later as we get going. But in this case, we have 4 or 5, or sometimes even 6 planning agents flying around with a bunch of dynamic obstacles as well. So it's good size room for doing motion capture type experiments and then building up from there and thinking about how other types of sensing comes into play. So what we're thinking about then is autonomous UAVs operating in dynamic environments such as this. Could be because of things moving, could also be because of things like wind and so on. So sort of just worlds that are different. And so you're facing sort of the issues of real-time trajectory planning and doing collision avoidance while thinking about sort of performance optimization for the task and so on. Again, dynamic obstacles. So you're thinking about fast adaptation to the motion of those vehicles themselves. Robustness, trying to cope with sort of localization uncertainties. I mentioned this motion capture, but we often use onboard sensing as well for actually determining where the vehicles are. And you'll see me talk about determining where the other vehicles are, which is also one of the main sources of uncertainty in this work. Obviously, scalability comes into play. So we're looking at things which are sort of not just, single vehicle or when don't scale up, but think about something that can go up to, 10, 30, 50 type vehicles if we could. And the primary sort of issue we've been trying to face is that it is quite possible to pose these as optimization problems. In fact, you'll see us do that. The question then simply becomes a case of, can you implement those and solve them fast enough in real time so that you can have the adaptation and robustness that you want to be able to demonstrate. So you'll see us use these and we'll pose them, but we'll also highlight some of the challenges of using them. And if you can solve them, but it's too slow, then that slowness leads to an inherent risk, and you'll see how that comes into play. So, sort of given that as a sort of an overview and setting the stage, what we're then talking about is the techniques we've been looking at to address this. I'm going to start primarily thinking about single vehicle stuff. Sort of give the foundational work in the context of that, and then towards the end, begin to talk about how this spills over into multi-agent as we go. Okay. So the main topics then we're going to talk about Panther. Anytime you see words with PA in it, that stands for perception aware. So Panther, and then we'll talk about Deep-PANTHER. There's a Panther star thrown in there somewhere, but basically what it's primarily thinking about is so perception aware. The issue is we're in a dynamic world, we're flying around in it, but because of the inherent uncertainty in what's going on, not so much what we're doing, but what we think is going on around us, we use the onboard sensing capabilities of the vehicles then as a mechanism to actually track and see what else is going on around it. So if you're concerned about the level of uncertainty, then you could try to address that directly. So it becomes thinking about sort of an information gathering problem in the context of path planning, obstacle avoidance. Talk about the robust MPC policy distillation, sort of how to get from planners to thinking about implementing things on neural net framework. And then, like I said, the primer is the multi-agent version of that. So we'll get down to that towards the end. So we're trying to cover these three topics. Like I said, the first two primarily, almost exclusively single vehicle stuff, span sort of the main technologies, and then the primer builds on that and uses them as we move forward. Okay. All right. So here's Panther. Let's talk a little bit about what we're trying to accomplish. So this was sort of one of the original sort of motivational type videos that we made. Probably this is 7 or 8 years ago now. And the idea was, could you fly in this world with a finite horizon sensor, so you don't know really where all the stuff is, and there's just a bunch of obstacles moving around. And the question is, can you fly through that world and survive? Right. So it's clearly a planning problem, but also sort of an inherent sort of, hey, there's uncertainty here. I don't know where all this stuff is. And so with onboard sensing, you might be thinking about where to look and how to actually track any of these objects that are in the vicinity in such a way that you can more precisely know where they are, but also then make a better prediction of where they're going to be. So I'll show this video again later, but just to sort of give you a sense of what I'm talking about here, there's a vehicle flying around trying to avoid the other obstacles in the world. There's no idea where they are. And it's using onboard perception then to figure out their state, which includes obviously position, but also velocity, and then try to use that in their prediction sense to then plan a path around it. So the idea then is to be thinking about perception aware planning. So again, it's my path. So I'm doing obstacle avoidance, but I'm also thinking about where to look. Now, with these types of vehicles, as you probably know, if you have a forward-looking camera, yaw of these vehicles is really irrelevant. So you can sort of use that as another degree of freedom to turn and look somewhere, right? But there are physical limitations on what you can do, and the physical limitations of turning actually then start coupling into the physical motion of obstacle avoidance, because you only have so many thrusters. And you can't just use them all completely independently. So they're sort of dynamically decoupled, but coupled through the constraints. So the idea then is to think about dynamic obstacle avoidance while we're thinking about perception aware. Now you can decouple these things, right? And you basically just say, I'm going to plan a path, and then I will just look, do the looking task afterwards. But and that's okay. It just leads to potentially really poor obstacle predictions because you're not necessarily thinking about the best places to be while looking. And again, remember, we're not just looking at one thing, we're looking at multiple things, and yaw has yaw rate constraints. So you're not just looking at something, you're looking over here, looking over there, and you're doing a bunch of different yaw types of maneuvers while you're doing this. So coupling yaw choices for the where to look into your position choices leads to less conservative type results. And you can do that. I mean, if you ignore perception aware, you get bad estimates. You decouple, you can get sort of It sort of tends to be a less computational intensive operation, but it can give you conservative results, in part because you're just not getting as good estimates as we can get. And what we want to try to do then is try to reduce that conservatism. Could we find a way to make it so that the path planning and yaw are actually coupled together, and we're thinking about perception-aware path planning with obstacle avoidance, while ensuring computational tractability. Now, if you know about these types of problems, you should already be thinking, oh my God, that seems like a really complicated optimization problem, and it is. And this is it, and don't want you to read any of these equations, just look at it and go, wow, that looks complicated. That's enough. If you take that away from this, that's good. Because what you have is a bunch of dynamics, that's the easy part, to be frank, and then a whole pile of constraints, which again, you can have those anyway. The challenge really starts coming in when you have this sitting in your optimization problem. It's is something in the field of view type problem. It's a pointing question that's explicitly in your optimization. This is now coupling the nonlinear dynamics of attitude with the position dynamics of motion while you're trying to do obstacle avoidance of something that's moving and isn't just a point solution. It's thinking about prediction forward in time. So high complexity here. It's not like, the end of the world, sort of super duper, impossible, but it's just high. So the question that we had was, if we try to implement this, it's just going to be too slow. So could we find a way to speed it up? And so then started thinking about whether or not we could learn the result, i.e. this is a planner. The question is, could you learn the result of the planner and encode it as a policy? With the idea being that the inference of the policy is way super fast. You just need to convince yourself that it's accurate enough, right? So we're going to try to use learned neural networks as a policy, encoding the model-based expert, which is basically this here. Okay. So that's essentially what happens. Is we're trying to learn the fast neural net policy from the perception-aware planner. Basically try to reduce the conservatism of doing decoupled perception awareness. And so we're going to go from, the team would use different phrases. So Panther's this thing I'm talking about. Panther Star is a better version of that. And the Deep-PANTHER is the one we're trying to learn. Okay, so it's sort of orange to green to pink to red, I guess. But again, when you're doing this, again, imitation learning, if you don't know what it is, I'll say some words about it. But basically what it has is an expert, which is the planner. And then it has a student, which is just basically trying to replicate what the expert did. And you essentially end up with something that looks like this. I mean, you basically have an expert that's doing something, and then the student's just a neural net. And you look at the outputs and say, are these the same? And the premise is, if you have enough data, then you should be able to replicate, all the sort of interesting cases the expert might have been asked to investigate. You have an answer, and then the student just has to replicate it, right? Sounds easy, right? Of course, it's not, right? So the main challenge with imitation learning, it's been around for a while. The main challenge is, just how much data do you need? Remember, all of these optimizations are doable, right? I mean, it's not like this is impossible. You can do it. It's just super slow, which means you got to generate a whole pile of these things. And also keep in mind the dimensionality of the space we're talking about is enormous, right? Because there's a lot of stuff going on in this world. It's not just us moving in the static world. There's us moving, there's things moving. So you've got to replicate tons and tons of different scenarios to actually capture the full gist of what it is that this expert would know. Again, the expert being the planner. If you ask the expert any one of the questions, it could give you an answer. But there's like many, many, many questions. And the idea then is, how much data do I have to collect to be able to replicate the knowledge basis from the expert really have, and capture that in the student. So that's sort of the data issue. The other issue then is, can the student actually learn it well enough, right? And that turns out to be an issue as well. A niggling issue that's lurking in the background, which we didn't actually address that particularly well in this work. You'll see we'll take a little of a shortcut, and I'll talk about that in a second. But it's actually addressing the constraints that are inherent in this problem. So there are some constraints in here, and they got a little bit relaxed in what we did here. So we ended up solving some of the dynamic constraints that were not imposed as crisp, hard constraints. So the potential was we were learning things but not dynamically feasible. That's still out there as an issue, but I'll point to reference 3 here, Rayan, which is work that came after this. It's still, they're actually still finishing the paper. It's on arXiv if you want to take a look at it. Very cool work. Doesn't address everything here, but it explicitly talks about how to learn a neural network while imposing convex constraints on the neural network simultaneously, such that the answer from the neural network is ahead of time, is guaranteed to satisfy those constraints at the end. It's not just a case of test and see, it's a case of you learn to satisfy constraints, which we were not doing in this work here that I'm talking about, but we have done it since then. But this work sort of skipped that issue. Okay. All right, so that's roughly what we're trying to do. You have this expert, the planner, and the idea is if we can cut down on how much this planner has to do, then we can do this in a tractable and a computation time offline. The students enroll in that. The idea is that when we implement this, we should be wicked fast when we get online. All right, so that's the idea. Built into all this, and other people have been looking at this for a while now, and you'll see this show up a couple of times. Dagger is a sort of domain augmentation, data augmentation, which is sort of methods that people have been thinking about how to create, essentially avoid this need to create lots and lots of different data pieces to learn from. And so we have, in the work I'll talk about next, you'll see how we sort of build on these types of ideas. For the Panther, Panther Star, and Deep-PANTHER, there was a little less innovation at that point. It was more a case of demonstrating to ourselves that this would actually work. So we ran into, and the issue, the reason why it wasn't obvious that this would work is that when we first started doing it, we ran into something sort of head on that in hindsight seemed kind of obvious, but at the time was not, which is that if you're trying to learn how to do obstacle avoidance, it's sort of interesting, right? Because I mean, you look at these pictures and you think, well, like look at case number 2 here. There's actually different ways to go around an obstacle, right? You can go to the left, you can go to the right. And then you have a student who creates an answer, and then you sort of evaluate the student answer compared to the expert answer. And unless you knew whether or not the student was trying to go to the right, it may be that it was actually trying to go to the right and actually went to go to the left. And then you just sort of score that based on how close it is. Well, it may be that distance-wise, it's not that far away. So you say, okay, it's not great, but not horrible. And the issue that we started having was that the student ended up learning the average of the expert, right? The experts could go to the right, they go to the left, they go up, go down, do lots of different things. The student just basically ended up learning the average. And the average of things that go left and right is actually fly right through the middle. So we ended up with a student that was learning the exact opposite of what we wanted. And it just was not a problem that's going to lead to a tractable solution for the student. And like I say, in hindsight, perhaps obvious at the time going into it, I don't know that we realized this was going to be as big a deal as it was. So then what you actually have to do is try to figure out, and that's sort of what's going on over here in this sort of assignment problem. The student gives you a solution, and what you're trying to do is to assign that solution to a type of expert solution. Is it sort of the equivalent of left-right? And then grade it based on the quality of sort of left-rightness. As opposed to just generally having a whole stack of student solutions, a whole stack of expert solutions. Because if you do that, the student will just learn the average and fly right through the middle. So what you really have to do is to be able to bin these things into different types of solutions. And of course, it's not just as simple as left, right, up, down. I mean, you basically have to figure out a whole spectrum of different types of things that differentiate the expert. We literally are then running an assignment problem within that, trying to associate each of the types of student solutions with what the expert was doing based on these features, and then from there back out just how good an answer it was. Then we sort of effectively grade it, and then that gets fed back into the learning exercise. So like I said, that was explicitly required to make sure the training loss was being computed correctly. And when we did that, then we're able to get a student that could actually figure out how to not fly into things, which was good. Okay. The other thing was I mentioned the dimensionality of the state space and the issue of constraints. The way we sort of sidestepped it here was, one, we actually just learned the trajectories, and then Jesus, who did this work, backed out the fact that for a given object he was looking at, he could then figure out exactly what the yaw angle should be from that. And so, although we're learning a coupled result, in the training, we're actually only training X and Y. It's X, Y, and Z, essentially the position. And then given that position of the quadrant, which is to say this thing here, we can then tell you what yaw angle must be, and that's in the training. What is then, but this helps us keep down the dimensionality of what we have to learn. And if you've done learning of this type, that the bigger the thing, the dimensionality, the neural net, the harder the learning gets. And this is part of the challenge for this work. So this is sort of accurate, but it's less conservative than completely decoupled. It's just not the perfect sort of thing we had set out to achieve at the beginning. So it's an approximation, but better than decoupling. Let's put it that way. Okay. So how does this work? So this is the video you saw, and so the answer is it works really well, but perhaps more importantly is this picture over here on the left. This is the cost versus replanning time. And this is where we started with Panther. We then made Panther better. We got Panther Star. And anytime you get better, it typically gets slower, as is indicated by this. So we had something way better, way slower. Couldn't implement this. This is 10 to the 3 milliseconds. You're up over a second. There's no way that's going to survive in this environment. This is going to go around whacking into stuff. So basically, the idea is that now we did Deep-PANTHER, which is just described to you how we accomplished, and then ended up with this red pile down here. And it's not quite, it's 2 orders of magnitude improvement in computation time, but you're now down to 20 milliseconds, which is quite reasonable for these types of environments. And so this is like I said, the vehicle flying around. You sort of see the field of view up here of what the camera is as it's flying around looking at stuff. This is obviously what the camera is. And then obviously it has doing some VIO operations as well in some of the experiments. And that's the reason for the green carpets on the ground, so you can actually track some stuff and actually see where it is as well. So like I said, this was good news. I mean, this basically meant that the whole philosophy that we had, or thinking about a strategy for cutting down the computation time for these high order optimization problems seemed quite realistic, and we could get from up here in seconds down to milliseconds quite easily, and do quite complicated collision avoidance problems through learn policies, as long as we paid attention to things like the collision avoidance and things like that. So about that time, and Andrea joined the team and was so that was sort of the end of Jesus's thesis and his typical sort of new student startup, and Andrea was working with him and began to see the tail end of that exercise, and began to think about where can we go from here, and where he ended up going. And I won't get to the full end of the vision base because that'll make this talk about 2 hours long. So I'll give some pointers to papers at the end. I won't get to this other piece down here. I'll just talk primarily what Andrea did here, which was, again, a huge innovation in terms of just a step forward over what what we just described, which I think was a nice demonstration of the use of imitation learning, but it wasn't necessarily there was much innovation in the imitation learning itself. But that's about to change. So when Andrea sort of said, well, look, what we're implementing is the classic, robust controller, the attitude controller, doing some kind of state estimation, possibly system ID to do adaptation, and possibly doing vision feedback and things like that. What we'd like to do is replace the entire thing with a neural net, basically just the entire thing. And that was his model. And so, effectively the end-to-end type learning that you've probably seen in labs such as Scaramucci and things like that. The question is, could we get to that type of full result? And I won't have time today to go through that entire piece. He did get there. And there's some, like as I pointed at the end, so papers that describe the entire thing. I'll just focus on the planning part of what he was trying to do. So again, the goal, learn policies, with robustness and performance that sort of comes from MPC and the model-based planner. So doing the predictive control into the future. And horizons maybe of 40, 50 steps, thinking about how to robustify that. And so if you're familiar with the concept of robust MPC, then robust tube MPC is sort of something comes with that. I'll talk about that in a second. And that was sort of the basic framework he's looking at. And the inherent question was, could we learn something that retains the robustness of robust tube MPC? So the idea is that MPC is a good way to do planning, but it's a path. Robust tube MPC is thinking about a way to robustify that. Could the planner retain that robustness? If it could, that means the probability of success is when you go to the real world is that much higher. Okay, again, imitation learning is going to be the framework. Data augmentation, already talked about that. But what's particularly interesting about what Andrea did was coming up with a sort of a unique way of thinking about how to do that data augmentation, which again is tube guided. So we end up using the tube that comes from the robust tube MPC as a methodology for guiding how the data augmentation is done. And I'll give you a sort of a snapshot of how that's actually done. The result's kind of cool. And he's able to go from a single demonstration in simulation. So you give me one sort of idea of what it is you're supposed to do in simulation. From that, do the data augmentation, create enough data he can then learn a neural net policy, take it into the lab, implement it, and it'll work. And he's demonstrated that on multiple different vehicles that he can actually go through that sequence. And so it's handling the sim to real transition as well as the sort of just, model to real world transitions at the same time. So how does it work? So again, this is sort of generally what I was describing. So the red line is if you're doing MPC, you're just designing the path. If you're doing tube MPC, you're thinking more about this gray thing. And so you're thinking about, I'll keep you inside that tube, or I'll try to, and the understanding that there may be other things going on, like disturbances or uncertainties that are creating sort of variations around that. So you're sort of somewhere in the vicinity of the red thing, but you're doing something, away from it. And the point is that, if you have wind and whatever blowing, you can expect disturbances like this to happen. And like I say, what we're trying, that's in the whole sort of world of robust tube MPC, that would be the mental model, what you're trying to accomplish. And we're trying to see whether or not we can replicate that. And furthermore, use what's going on in this picture to help us do the data augmentation process. So here's a classic sort of picture of the kinds of things we're trying to do. So number of demonstrations used in training. And again, just to be clear on terminology, demonstrations is sort of a run in the sense that I give you a piece of data that says this is what the answer looked like, or I run the optimization once in particular, and get sort of a demonstration. But that's distinct perhaps from the number of data points that are actually given to the learning algorithm, because we're doing data augmentation, we actually enhance the number of data points that are actually given to the from that one demonstration. And so what we're thinking about here is robust tube MPC is going to survive. They can do this 100%, so it has no problems. But here, what we're thinking about are other techniques and other baselines that are actually struggling a little bit to actually figure out how to get the answer. They're not doing that badly, but it's taking as many as sort of 5 to say 6 demonstrations to actually get the answer. And this is a figure 8 with just sort of different initial conditions, what have you. But that's no wind. And then you turn the wind on, then things get a little bit worse, right? And so the basically now success rate, for some baselines is pretty poor. Others just degrade. They still sort of survive eventually, but not doing that great. So the idea was, this is all the picture of what the baselines were like when we started doing the work, and then what we're thinking about was, how can we improve upon that? So let's talk a little bit about what we actually do. So the way we get our augmented demonstrations is we go back to the tube. And again, the way this whole tube works is that inherent to these MPC algorithms is you're not just designing a path, you're actually designing this thing called the ancillary controller, which is a low-level mechanism that tells you how to essentially keep the system within the tube. That's sort of part of parcel of what comes with the robust tube MPC algorithm. You get 2 pieces. So the path and this other low-level controller. And that's sort of shown by these green lines, effectively. It's sort of like if you were here, the ancillary controller would execute something in the next time step that sort of keeps you back inside that tube. It's just something that just keeps acting. But the net result of that is we actually now have a way of creating these extra data points because we basically have additional state action pairs that come from, say, if you were here, the ancillary controller would say, well, do this. And so we get another data point, which is X prime and X star plus and U plus. And so we can use these extra sort of ancillary controller then to create these extra data points from the one demonstration that we got. So we know the demonstration is good because it's the result of the expert. Now we can embed additional data or extract additional data points from that and stack them all up and then go off and train the policy, which can now replicate effectively the entire tube. But we don't need to sample everywhere. We just create a bunch of samples, and from that, say at every time point along the path, and then we can then create these extra data points to learn from. So the states give us the tube, the actions then give us this ancillary controller, will come from the ancillary controller, which then enable us to sort of keep sort of very efficient sort of learning strategy in terms of we just don't need that many data points and demonstrations to learn from. And then furthermore, we are inherently learning something that's as robust as this tube is. And then the result then looks like this. This is what we get. So our result is in one demonstration, we get 100% success rate and we're good to go. And that's without disturbances. And then with the disturbances on, the answer is exactly the same. In one demonstration, we get 100% success rate, and then we're good to go. And let me show you kind of what that looks like in, well, again, just to summarize. So that converges after only one demonstration, and the answer is robust, which means that when you implement it, it actually works. So this is kind of what it looks like in the lab. Here it's flying around. And basically the point is that you're here, we're doing figure eights, here we're doing circles. There's no wind on right now. This is the leaf blower over here. And if you know, leaf blowers are pretty strong. So when you turn them on, it's like a howling gale. It's about 6 or 7 meters per second when you're standing right next to it. So it really is a pretty strong disturbance for a vehicle of this size. And so you can see some obvious sort of variations around what it's supposed to be doing. On the other hand, it's still staying within the sort of the bounds of what we're expecting. So real world demonstration of robustness based on a single demonstration that was done in simulation. And it could more from the real robot, depending on which one of these things we're doing. But the point is we can do it from a real simulation. Onboard inference, about 30 microseconds. So it's about 200 and maybe 250 times faster than the robust tube MPC calculation. And the cool thing is that this thing really seems to have an inherent robustness capability. It seems to be able to not just do this. We give it other things to do. So we trained to learn how to do this, but also knows how to do other stuff as well, which is really, really super cool. So a lot of people ask questions like, well, why do you do this? Like, what are the primary benefits? And after a little bit of exercise on the computation side, these are the kinds of numbers that we see, is that if you're implementing robust tube MPC, say as a function of planning horizon, so as the planning horizon goes up and gets bigger and bigger, not surprisingly, computation goes higher and higher. These are in seconds, so this is now up into, so this would be a millisecond, this is sort of tens of milliseconds. So these are not bad numbers, but we're down here. We're down in tens of microseconds. So our inference is basically is minuscule compared, inference time is minuscule compared to what's required up here. And if you've ever wondered why you'd want to do something fast, well, try doing any kind of control calculation with a vision system on board, and you'll want to do it fast because you have almost next to no computation time because the vision system's using it all. So you free up computation for all kinds of other stuff. It's quite conceivable now you can implement this on very small computers. These neural nets are not particularly large, they're sort of hundreds of neurons. And so we can implement these on quite small devices. What's also cool is the training times come way down. We're sort of here, Dagger plus the SA sparse is sort of our result. And so, again, trajectory length in steps, traditionally we're sort of in this range. And again, we're now down to quite short time training times, 20, 30 seconds, which again, if you're interested in doing things which are sort of explicitly adaptive in the sense of, the world changed, collect new data, then you can come in and retrain. But you're not looking at training overnight or anything like that. So very fast updates if needed. And again, it's just, these aren't terrible times, but these are up in the sort of 150 seconds. And so if you, doing it repetitively, it can be slow. Here, we're quite a bit faster. So the combination of fast inference time, fast retraining time, real wins here. The robustness of the real world demonstration, also super cool. So that's single vehicle, not particularly agile. And of course, classic, advisor, you say, well, that was interesting, but everything's kind of flat. Let's really push the boundaries, see what we can do. And as soon as that happens, everything goes nonlinear, and all the linear stuff I just talked about doesn't get thrown out the window, but it becomes a framework. And you say, well, does this framework generalize to nonlinear? And unfortunately, the answer is not really. The main reason being that the nonlinear robust tube MPC that exists, you can read about it. And the first thing you learn is that the ancillary controller is another nonlinear MPC. So we're trying to cut down the computation time and the learning process. When we did it in the other case, the ancillary controller was a pretty simple thing equivalent to LQR, dead simple to implement, not a big deal. But a nonlinear MPC, yeah, that seems kind of hard, right? So this isn't really going to work. So what Andrea did was take a look at how to fix that. Basically went through the process of essentially thinking about how to come up with a sensitivity-based linearized controller that would still work, and then enable us to get to a nonlinear implementation. That's basically what they ended up doing here. So basically use a time-varying linear approximation for the data augmentation process, and then did an additional step at the end of the imitation learning, which is sort of fine-tuning based on reinforcement learning, where we basically go in and say, okay, well, given what you've just learned as a baseline, let's build on that, refine it, and make sure we sort of rough out any of the, any of the weaknesses in the final result. And so it takes a little bit longer to train as a result, and I'll show some results in a second. But what we're able to do now are things that are much more agile, much more acrobatic in what we're trying to accomplish. And our sort of definition of agility and acrobaticness is, essentially whether or not you can have much larger deviations in the angle of the thrust and the gravity vector. I mean, if they have to be aligned to basically stay afloat or in the air, that's pretty boring. What we want to be able to do is to really cant over and accelerate quickly, and so you'll see that in some of the videos I'll show in a second. So similar results to what I described before, number of demonstrations versus success rate. You want to be up here, no demonstrations really fast. And if you're wondering what that pink line is, yes, that's ours. So we are up here. Again, it takes a little bit longer. It's not quite one demonstration, it's sort of 1+. But again, compared to the baselines, we're doing particularly well. And others are just, struggle, and well, some struggle and others struggle less. Let's put it that way. Okay. But we are doing really, really well. And the ones that do well, this sort of green line here, they get to a high success rate, are taking thousands of seconds to train, which ours is not. Okay. Ours is sort of in the hundreds. So reduction in training time, as well as achieving sort of high success rate with few demonstrations, is a big plus in what we're able to do. Keep in mind, a demonstration in the context of this, if you were working with a real vehicle, 25 to 50 demonstrations means you have to fly the vehicle 25 to 50 times doing this. It isn't like you just do it once and then look at it. You're literally out there flying it 50 times. So this is a real time cost down here. And so being able to do this in 1 or 2 demonstrations is a real savings in terms of laboratory expense. And so this is a big plus in terms of moving forward. So like I say, ours is about, 10 times efficient in both data, training time, and far better than the best imitation learning that existed prior to what we were doing. DR is domain randomization, which is another way people bring robustness in. The robust tube MPC that we're doing in our demonstrations is a far superior way to accomplish that. All right, so what does that look like? So here we are in the lab, back with the quad rotor, and now we're doing things pretty aggressive. We're doing a flip. So basically what we've learned is to flip over. This is what it looks like on board. We just go up and just flip like that. And it's pretty fast, but as you probably realize, pretty agile. And then just to sort of demonstrate how robust the thing is, we, for instance, put that mass on there and knew nothing about the mass. We didn't tell it about the mass. It's moving, it's kind of in the way. And furthermore, it's not even a taut mass, like in the sense the string isn't taut, it's just moving around. And then to demonstrate this is repeatable. This is actually 5 demonstrations in a row. Just sort of take off and go and do it. And the last one had a low battery and it bounced off the thing and then popped back up again and recovered. So success-ish. But like I say, with the slung load, it's pretty cool watching a flip with a slung load because it actually does quite successfully put on extra drag. And again, these are not things that we've told it about. It's not like we said, oh, and learn how to do this with extra drag. It's just that we just showed up and said, exact same neural net. By the way, let's put the extra drag on it and see what it can do. And again, that flipping motion is fast. And so these big things underneath are creating quite a lot of drag underneath. So again, just to demonstrate just how robust this capability is, even though we didn't tell it that this is what it's supposed to be doing. Kevin Chen joined MIT a couple of years ago, and he's working on the SoftFly. I can't do justice to his description of this device. It's very cool, very small scale, basically about half the size of your finger. And you'll see a picture in a second. And so one of the questions was, can we demonstrate transition of this work to that capability? And so this is what Andrea began to look at next. Same picture. Explicitly, though, what we're looking at now is bringing much more of the position and attitude control. In the bigger vehicles, we tend to keep the attitude control separate, although we have also learned that most of what you saw there was separate. Here, we're explicitly doing them together. And so the whole thing is just one big neural net learned position and attitude controller put together. The result then looks like this. That was it. It's really super fast. So I'll show it again, but I'll show it slowly so you can actually see what's going on. In part to show you just how agile the thing is. So this gets into that about a 45 degree. It's essentially a bang controller, as you might expect for sort of high speed point A to point B, but it does a really nice job, and it's able to fly. I think let's see. I think the numbers come up about 1.25 meters per second, which are 4 times faster than the state of the art of flying something of this scale. So again, very complicated aerodynamics, which we really don't know that well. We do a reasonable job of learning them and then stick robustness around the rest of it and say, make this work. And this is the end result. So nowhere near finished on this yet. We're still in the process of doing a final sets of demonstrations, but this is some of the numerous results and newest capabilities of this system. So Andrea's work, and I mentioned what he had done in terms of we did the trajectory tracking, we did the sort of nonlinear stuff, we took it to the extra vehicle, the vision-based flight. That's the part I can't talk about at all. It's like it's an entire another talk, really. Just mention the complexity of doing it is that if you're going to do data augmentation and you're using vision-based systems, you have to figure out how to augment the vision sensing capability of the device, because it's looking at something. And here, when we in the prior work, we said, well, if you move, then I have an ancillary control that tells you what's supposed to happen. So all I have to do is to say at this position, what would be the control, and I get a new data point to put into the learning. Here, what you have to figure out is if you were here, what would you see? And so I can't just talk about I'll move you and then say what's the new data. The new data has to involve a new observation, and to do that, you then have to have a model of what you are looking at. And of course we don't, so then you have to make that. And so that's why the title of this work is Tube Nerf. And what we used obviously then was a nerf. And so this was last year's thing that everyone was excited about was nerf this, nerf that. This year it's all about Gaussian splats. So I'm sure we'll have a Gaussian splat tube something next year, but right now we're just using nerfs. The thing I will mention is the bottom right. So there's a paper on this, and I'll give you a reference at the end. But the thing I did want to mention, because it's got a cool video, is one of the things that had always challenged us about this neural net. Yes, it's particularly robust and seems to work very well, but models change and vehicles change. Can you learn to be adaptive? And adaptive here is a slightly different context than you might think of. Adaptive control, you're typically thinking about literally changing the control. Here, we don't want to change the neural net, but what we'd like to do is have the neural net recognize that if we feed in a different signal, that what it learns, essentially the output of this phi here, or the z variable, is it uses z as an indicator of, hey, something's not going right. And if that's not going right, then I should behave differently. The neural net is not physically changing. It's the same neural net, but embedded inside the neural net is now essentially different types of behavior, and effectively knows how to modify the output, the control signal u, based on this additional signal z hat that is measuring, and that becomes the adaptation of this neural net. So again, same type of experiments I showed before. Here's a vehicle flying. It's just hovering in this case. We show up and then just start doing all kinds of weird things to it. So we added slung load, knows nothing about that, but it can adapt to that. So then we broke a propeller and just turn it off, as indicated here. It's now turned off. Doesn't know about that, but just adapted to it. Then we turn on the leaf blower. Again, knows nothing about that, and yet adapts it as well. And so the flying doesn't look particularly pretty, but again, you have to think about just how many things have gone wrong here, and yet it's still able to hover pretty well, which I know is not a particularly difficult challenge. But if you work with these types of vehicles, you know that things go wrong really badly, right? Like if there's a problem, it just ends up in a big pile of stuff on the floor. So the fact that it was able to robustly survive the repeated sort of breaking of various things in the system that was quite challenging. One of the things that's interesting about this is that I believe it's doing VIO while it's flying, and this hung mass is actually in the middle of the camera. And so we're not just playing with the dynamics of the vehicle, we're actually playing with the whole sensing system as well. And it's really quite cool just how robust this entire system was. All right. So everything I've set up to now has been single agent. Let's talk a little bit about multi-agent stuff. Let's see, we've got about 15 minutes left. So we'll try to get this done in, say, 10 minutes. All right. So much of what we're aiming for here is decentralized, asynchronous, perception aware. So we're going back to the sort of basic concept of we're now agents flying around, which are the things here where sort of these guys, well, this is one of them, this is the other. They're essentially little grids that are here. The green, whatever shape that is, pyramids, are the fields of view of the cameras that are on board, and the two brown boxes flying around with the obstacles. And so the idea is for these vehicles to be doing collision avoidance, so you're flying around, not hitting each other, not hitting the boxes, while at the same time making sure you sort of keep the boxes in the field of view so you can actually know where they're going, right? So the idea being it's hard to avoid something when you know where it is. And since these boxes are not reporting their positions, the agents are. The agents are reporting positions of plans to each other, but we don't know where the boxes are. And so if you want to not hit the box, you better look at the box. The challenge, of course, is that, if you go past a box, you don't want to keep looking at it necessarily. You want to be looking at where you're going. And so what we want to be thinking about was a balance, a trade-off between looking at things that actually matter to us versus looking in the direction that we're going, right? So it's sort of, well, how do you decide which is which? In the original Panther work, I pointed out that term in the cost function that explicitly costed is something in the field of view. And so in that case, it would fly around looking at stuff because it wanted to keep it in the field of view. But again, that doesn't always make sense, right? What you want to be thinking about is, I want to reduce the uncertainty in things that matter to me from a path planning perspective. And it's that coupling of uncertainty in knowledge, in the future, like now and in the future, to path planning capability. The argument being that the more uncertain I am about the location of this object in its path, the bigger the uncertainty bubble I put around it, which makes my planning problem harder, and thus from a cost perspective might be poor. But if I can reduce that uncertainty, I make that bubble smaller, I can plan a tighter path, get better performance, and that's how we sort of cost the uncertainty. So uncertainty costs us from the perspective of increasing the path length because we have to fly around bigger bubbles of uncertainty. So that's how they were coupled together. And so we don't explicitly do what we did in Panther. So you have to look at things. We just said, look, if it's uncertain, this is how it's going to be reflected in the cost. You want to think about reducing uncertainty while doing the path planning. And so we're thinking about all these different issues all embedded into one. That led to a couple of different algorithms. So PARM, I believe, began as perception-aware robust Mater. And I'll talk about Mater in a second. And then it got better. So that was obviously PARM star. And PARM star was an optimized version of PARM, which was, sort of PARM was good, but PARM star was better, but ended up being even harder because it now explicitly became non-convex. And then primer then was a way to think, okay, well, that's all getting hard again. So similar to the path we have with Panther, can we get down to something that's imitation learned and then get it to be faster that way? And that's what primer is trying to do. Okay, let's talk about those various pieces then. So I mentioned Mater. I don't know if these videos are going to work. I was having problems with these before. That doesn't look good. Well, here's one of them. This is roughly what you saw at the beginning, but I think this one's on board. I don't know why the top one's not running, but and so it'll give you a sense of sort of what it's like to fly around in the lab. I mean, it's, doesn't seem that busy, but there's a lot of things flying around, and you're trying to avoid all this stuff and not hit it and plan paths. They're flying about 3 or 4 meters per second in these rooms, so it doesn't take that long to do a traverse. So stand around, look, they're planning a path. They see if they're able to go, and then they go shooting off. And you see vehicles get pretty close to each other, and it's full 3-dimensional path passing each other, and they're going around and above and so on. So it's quite a complicated environment. So what's inherent to Mater is that they're optimizing trajectories. They're thinking about things. They're mesh networks. It's all asynchronous. It's fully decentralized. So it gives a good foundation to build things on top of. And this video up here, if it ran, which it isn't, is just a bigger sort of simulation of what the environment looks like, and it's covered in some of the earlier papers mentioned down here. Okay. So what PARM's trying to do is sort of build on that, but bring perception aware into it, because what Mater had was none of that. Basically, it was all essentially we assume we know where these things are, and then don't have to necessarily look at them. So we're reporting obstacles in the Mater framework. And what we'd like to do is not do that. We want to use onboard perception as a mechanism to figure out what the things are that we're actually trying to avoid. Oh, okay. Well, now it plays. Well, yeah. Okay. So again, big challenge here is that one of the primary issues is that the number of things you're looking at any given instant is changing, which is not good, because at the end of the day, we're going to learn a policy, which is a neural net, which is a fixed number of inputs, right? There's sort of a vector. It's going to go in, it's going to do a bunch of multiplies, whatever, and then something's going to come out. And you can't have that input vector be changing with time. So there's different strategies, and we've looked at graph neural networks as a mechanism to solve this problem, and it's still continuing to look at it. It's hard to learn that, quite frankly. One way to get around that is what we've been using for quite some time, which is effectively an LSTM type framework. We essentially take a stack of this stuff, shove it into here. These can be variable, but this doesn't have to be. In fact, it isn't. And the net result is that what goes into here, the output of all this is fixed length. So this is essentially a smushing of all this stuff over here. So this can be variable. This is not. And as long as you basically learn the mapping from a variable set of things into the output vector. I mean, this is output, but I mean, so I guess it's this one here that's fixed. These are the fully connected layers that form the policy itself. This is the mapping from stuff to the input to the fully connected layers. So that's the framework I'm using. It's not, I guarantee, I'll admit, not the best framework, and it has its limitations, and it is also difficult to learn. Graph neural networks, I think, are ultimately a better strategy. We've not had as much success with those as I would like. Anyway, net result, you can basically do what I just described, where Parm star is the planning framework. We can then now get this thing is way faster, and it's about 5,000 times faster in terms of computation, which sounds good. It's just that the original was really slow. And so it was like, again, these are milliseconds. So it was like about 4,000 milliseconds. So 5,000 times faster than that is about a millisecond, which is good, but not like ridiculously fast. And these are sort of single vehicle results. If you scale up to things that are actually multi-vehicle, and again, the size of these problems gives you a hint on how hard these are to do. These are not big problems, and these are hard to learn. Again, the size of the space in which we're learning now is just enormous compared to what I've described in the past. So I described what we did with imitation learning on single vehicle stuff, very successful, but the size of the learning space is quite small compared to what we're looking at here. These are big problems in comparison. And so computation time, again, primer compared to Parm star, always much smaller. But even again, you can see now it's just not super fast, right? We're hundreds of milliseconds fast, not ridiculously fast. So again, there's big challenges here still to be addressed. And we need to find ways to make this, the optimization problems are too slow. That's still certainly true. And the learned neural nets are faster, much faster, but they're still too slow. And so we'd like this whole framework to get quicker to learn and quicker to implement. But the resulting neural nets are big, and the learning space is large. And so those are two real impediments to making huge progress here. Last thing I'll mention is that that's one axis to push on. Is just keep scaling that up, and we're sort of bigger computers and better strategies, and we keep pushing on that. Another thing that comes up though, and this is the next acronym is PUMA, which has the P and the A separated slightly. And the UM stands for uncertainty, something. I'm not sure. Well, I think it's perception aware, uncertainty aware, multi-agent. I think what PUMA stands for. And it brings in something that we're also very interested in, because my lab also does a whole pile of other work on perception-based SLAM, things like that. And one of the challenges that we often face with multi-agent systems is they don't always know where they are. Now, most of the agents in the world trying to figure it out as they go along. And so the whole framework for a lot of this multi-agent stuff is, I will share stuff with you. Well, the problem is that everything I know and everything I'm doing is in my frame. And everything you're doing and is in your frame. Well, these aren't the same frames. We're not working in motion capture frame. We're working whatever frame it is that you haven't figured out so far. But if you're running a SLAM algorithm, it's quite likely your frame and my frame are not the same. And so one of the things we have to think about then is, how do we align the frames between these multiple agents to make sure we can actually share data at the planning level? And that can be done, but if you've ever tried these types of alignment problems, it's hard and not perfect. And so that introduces an additional type of uncertainty. So now we have uncertainty in where I am, what everything around me is doing, people sharing stuff with me, but I'm not really sure how to use it because I'm not really sure what frame it was in. And it's like a lot of information. It's like, well, it's good only if I know how to understand it. And I don't want to be using information incorrectly, because then actually becomes bad information, which then corrupts what I'm actually supposed to be doing. So you want to be really cautious in how you blend everything together. So what we have inherent in this, and I don't know if I can replay the video here, but is a process by which these agents are actually doing an alignment step, which is captured down here in the part of the video, where they're actually trying to do frame alignment, make sure we're actually consistently aligned in our understanding of what is what and what's north and what's south and so on, which then allows us to use the shared information of the type that I was just describing to then plan paths, to then do perception-aware type collision avoidance. And so that's ultimately what PUMA is trying to do. And that's sort of ultimately going to be Coda's PhD thesis that he's now working towards. So that's sort of the holy grail of sort of tying together all the different pieces from both of the planning, imitation learning, the perception aware, the perception work itself, and bring all those pieces into play. All right, so covered a lot of ground. Like I say, Panther to Deep-PANTHER sort of was one thread, a bunch of papers there. Talking about the robust tube MPC, imitation learning. These are the papers that I didn't get time to talk about. One is the sort of the tube nerf, And then, of course, the other one is the ubiquitous, how do you use large language models to do all this stuff anyway, and not have to learn everything. So this is our contribution to that. And then the whole parm star, primer, and how to do decentralized multi-agent work of this kind. That's still ongoing with Puma now being the thing that we're currently working on, and then doing hardware demonstrations on basically as we speak this semester. All right, thank you for your time, and I'll stop there.
Thank you, Professor Howe. That was a wonderful talk, like giving a complete picture on how things work on all the ends. I really like the talk. So there is a question on about the tube MPC. So like,
Sorry, which
you
slide was that?
mentioned, yeah, about the tube MPC,
Oh, yep,
robust tube MPC. Yeah.
yep.
So once that is learned using a neural network, you mentioned that like you were able to consider a single demonstration and consider the tube around, uh, like sort of do sim to real transfer.
Yep.
And the question is, were you able to incorporate like dynamic obstacles in these situations? And upon incorporating these dynamic obstacles, would would it be the same when it comes to sample efficiency?
Yeah, and right, and so this work doesn't do that, right? This is, in fact, this doesn't even have any obstacles in it. This is more like
Mm.
flying in a world, and the things you care about are just the dynamics itself and disturbances. If you get into the obstacle world, you end up with a problem that essentially Parm and Primer are trying to solve, because they're doing dynamic obstacles, but even with static obstacles, you then have to think about collision avoidance of, say, a tube with an obstacle, which again is completely doable. I mean, you can pose that problem. That's not what's happening here. Whether or not you retain the same efficiency, I mean, I'm reasonably confident that the single vehicle stuff is quite tractable on the scale. Where we're running into most problems is on the multi-vehicle side of things. It's the dimensionality of the learning space is scaled so quickly upwards. And again, with the elements of perception work coming into play, there's a whole other thread you have to look at in terms of the where is stuff, because it's you have to if it's a static world, you just have to put something in there, right? But if it's a moving world, then you have to every different demonstration has to have a different place for that object. You can't just have it be in the same place every time. Otherwise, you end up not learning anything useful. So there's just another large state vector you have to randomize over, and it creates a lot of different types of many pieces of data needed to actually get a good result.
Yep. Thank you for the answer. And there's another question on when it comes to the adaptive position control. So looking at it from the perspective of reinforcement learning and like causal inference, there are this concept of confounding, where there are unknown factors that affect how your system evolves, and
Yep.
this disturbance from the air blur can be considered as such. And there are a bunch of works that consider sensitivity models, as in like if there was a high level decision maker which was aware of all of these disturbances, it would have made so and so decisions. However, at this point, like the disturbance was not observed, or like the confounding factor wasn't observed. And people consider sensitivity models as in like to what extent does this confounder affect the decisions
Yep.
of the
Right.
decision maker? Like on that end, how much or like to what extent formally can we consider these unknown disturbances into this application as such?
Yeah, it's a good question. I mean, one of the things that's interesting about this strategy is that you basically are, and again, it's a two-stage learning process we go through, right? Where you're learning this policy and then you're learning the adaptation. You can iterate, but basically you go through these two stages. But we basically using a very, it's all essentially like doing, you think about you get the state action pair that then goes into phi, which creates this. So it's like we're doing system ID like in real time on essentially a signal, which again, phi has been learned. We're not dictating what it has to be. So we just throw out a whole bunch of scenarios and say, well, we'll just randomly fail stuff left and right and move things around. And then it backs out from that. And we give it this data and it backs out from that what phi should be. It's another learned neural net. Like it's learning that mapping to figure out what the right signal is to give to the policy to adapt and learn how to change. And so it's kind of cool in the sense that it's not like we don't have to like we in the training we just randomly pick stuff, but we don't have to like work out what are the possible sensitivities or what things can even possibly go wrong. We're basically just the neural net is just learning how to replicate the right type of response to the failures that have been demonstrated to it. But like I showed the video where we were failing stuff like propellers and things like that. Like we didn't give any of those scenarios actually. Like those aren't trained events. Like it never trained on anything looked anything like this. Like there was no training where we said, oh, by the way, we might put a pendulum underneath this. Or I don't think we even trained on a propeller fail. Like it's like that wasn't part of the training set. So you basically just you're like training and failing different pieces, but the system has now learned an inherent ability to adapt to variations in what's coming in here, in the sense that it's the variations in the state action pair are understood as being indicative of there's something wrong, we need to fix it, and it knows how to fix it. And so it doesn't really matter where it came from, what caused it. It's just that that's the indication that there's a problem, and that's what it does to fix it. And when we went to the large language model, we basically used the exact same strategy, right? We basically took a signal like this and just fed it right into the large language model and said, here's the data, interpret this and tell us what we're supposed to do. And then it did. And it came back and said, well, things aren't going well. You should take this action. And so in that case, the large language model was essentially prompted by saying, if this is, if the system's supposed to be behaving well, and this was the data you saw, what would your, interpretation of this be? And it comes back and says, well, if it's not going well, these are the actions you should take. So it was a different version of adaptation than what I'm showing here, but effectively the same type of thing. So like I said, the advantage over, say, something that's the confounding models is we're not necessarily going through and enumerating failure modes and looking at sensitivities. We're just giving it the signal from which it can interpret what to do instead.
Yep, thank you. And one last question. So I worked with these time-dependent policy like you had in Primer, where you had the LSTM being fed with time-dependent data, and then it's going through a final connected layer for the outputs. So I'm just curious on how have you been able to incorporate like robust constraints, hard constraints on these sort of problems. Like because like when it comes to min-max learning and like robust reinforcement learning, there is always an issue of satisfying the constraint, as you mentioned earlier.
Yeah.
So what's your take on this?
Well, so I'm not sure I can give a solid answer to that because I haven't actually done it. If Coda was here, he perhaps could answer it, and maybe the short answer is perhaps you can ask him. Well, I mentioned the paper Ryan though, which is the algorithm that Jesus has come out with recently, which is putting in hard constraints, like hard convex constraints in learning algorithms. So he's doing things like I'm describing here, but he was doing it on a dog robot, and he was looking at joint torques as being things that you had to constrain to be below certain levels, and can impose constraints like that as hard constraints in the learning algorithm. And so there are techniques that are out there that enable that to happen, and that's not what this is doing, but it is conceivable that you can do that. It's actually really fast too. Rand's a really fast algorithm, and like I say, it's, convex only, so it doesn't handle everything, but that might be of interest. But on the other hand, it's enables you to capture some pretty cool types of constraints.
Yeah. Okay.
Okay.
Yeah. Thank you so much. I'll definitely go and check that paper out.
All right.
Yeah.
Sounds good.
Yeah. That's all for today. I think that was the last question. And, yeah.
Okay.
Thank you so much for giving us this talk.
All right. Perfect. Okay. Talk to you soon. Bye.
All right, everyone. See you next week.